Okay, so let us continue with this week's lecture. So we were discussing probability theory, and yesterday the point where we left off is birthday problem. So the problem was that in a group of n people, what is the probability there are 2 people with the same birthday? So of course you might think that there are 365 days in a year, so until and unless n is very large, this probability would be very low. But we calculated this probability, and we found that this is practical. In reality, it is actually fairly high for even moderately large values of n. So if you are 30 people, then the chance that 2 of you have birthdays on the same day is already exceeding 70%, and if you are 50 people in the room, then the chance that 2 of you have their birthdays on the same day of the year is actually exceeding 99%. So that's almost close to being almost sure. Okay? Okay, so this is precisely the slide where we left off last time, where we noted with surprise that if you are 50 people in the room, then the chance that at least 2 of you have their birthdays on the same day is more than 99%. Okay? So let us continue. So let us continue with the concept of independent events. So what is independence in probability or statistics? So suppose you toss a fair coin twice, would you expect the outcome of the first toss to influence the outcome of the second toss? So this leads to a very general and important concept called independence of events. So of course, if you toss a fair coin twice, it depends on whether the outcome of the first toss will influence the outcome of the second toss is not really a given or a foregone conclusion if just because the coin is fair, right? So whether such influences percolate from one toss of the coin to another is related to the important concept of independence of events. So let A and B be 2 events. So again, let us remind ourselves what are events. So events are two different kinds of, so events are specific kinds of occurrences in a random experiment. So for example, if you are rolling a fair die, then the phenomenon that you get an even number as a result of the roll of your die is an event. Okay? And if you think in terms of sets, then if your total universe of all possibilities, all possible outcomes, which we call the sample space, so in terms of that, the event is a subset of the sample space, so it is a subcollection of the total possibility of all possible outcomes. Okay? So let A and B be 2 events. So 2 events are said to be independent if the probability of A intersection B, which is A intersection B as sets, so in terms of regular language, this is A and B both occur, like the roll of a die is even and it is bigger than 3, is equal to the probability of A times the probability of B. So this relation doesn't hold always. In the special circumstance, if this relation holds, we say that A and B are independent events. Okay? So let us so any questions about independent events? So we will soon see some examples. So, but before that, we defined two events to be independent. But in the case of random experiments, it is natural to think of many events together. So then it's natural to talk about the independence of several events, and these are called mutually independent events. So A, B, and C are mutually independent events if for every pair you can write the independence equation, but you can also write the independence equation for all the three sets taken together. So probability A intersection B intersection C is the product of the probabilities A, B, and C. Okay, and in general, you know, if I take any collection of events, they are mutually independent. If you take any sub collection, and then the probability of the intersection of those sub collection of events is equal to the product of the individual probabilities. Okay, so basically, to summarize, independence is equivalent to probability of the intersection splitting as the product of probabilities. So let us go to the all important examples of independent events. So a fair coin is tossed twice. So in this case, what we envisage is that if a fair coin is tossed twice, so what are the possible outcomes? So what is the sample space? It is HH, HT, TH, and TT. H standing for head and T standing for tail. So then it's a completely fair scenario. So all the possible outcomes have equal probability, right? So each of these possible outcomes have equal probability mass 1/4. So then A and B are independent events. So what is A and what is B? A is the event of getting a head in the first toss, and B is the event of getting a tail at the second toss. So let us now verify that they are actually, of course, if you believe that you are just taking a fair coin and you toss it once and then you forget about everything else and then you toss it again, of course they should be independent according to common sense. But here we already defined a formal notion of what it is to be independent as events in probability, and what we will see is that this natural intuitive notion of independence actually corresponds to our formal notion of independence. So in the case of tossing a fair coin twice, we will see that getting a head in the first outcome, getting a tail in the second outcome is, on one hand, it is intuitively they should not depend on each other, but also we will see that in terms of the exact probabilistic concept of independence that we just studied in the previous two slides, these two events are actually independent. In other words, they satisfy the independence equation. So probability A intersection B will be equal to probability A times probability B. That's what we are going to verify in a moment. Any questions? So let's in order to verify the independence equation, probability A intersection B is probability A times probability B. You need to calculate all these probabilities and you need to check that this equation holds, right? So what are these probabilities? So what is probability of A? So what are the outcomes which favor A? So the outcomes which favor A is getting a head in the first toss. So the first coordinate should be H. So HH and HT. These are the outcomes favoring A. So what is the probability of A? So out of total 4 possible outcomes, 2 outcomes favor A. So it is 2 out of 4, that is 1/2, half. Similarly, getting a tail at the second toss, again the outcomes which favor this event are HT and TT. So you can similarly calculate the probability of B to be 1/2. And what is the probability of A intersection B? It is getting a head in the first toss and getting a tail in the second toss. So the only outcome that favors this event is HT. So A intersection B, if you think of it as a set, is HT. So the probability of A intersection B is just this one outcome out of 4 possible outcomes, so it is 1/4. And lo and behold, probability A intersection B is 1/4, which is exactly half times half, which is probability A times probability B. So indeed, on one hand, these two events A and B in this experiment, in this particular case, are intuitively they should not depend on each other, but we just verified that under a natural probability model, they also satisfy the notion of probabilistic independence that we studied just now. Okay? Any questions? So let us continue with other further examples of independence. So fair coin is tossed twice. So let's see with the event of getting one head and D with the event of getting at least one tail. So C is the event of getting at least one head and D is the event of getting at least one tail. Are C and D independent events? So fair coin is tossed twice. It's the same random experiment, but we are now looking at two other events. Okay. So these events are the event of getting a head, getting at least one head, and the event of getting at least one tail. So, so if you think intuitively, it's not clear whether these two events are going to be independent, right? Because they might depend on each other, right? Because at least one head, so you have two tosses and at least one head, so it's kind of complicated. It's not as simple as getting something in the first toss, right? So it's at least one head, so it could be a head in the first toss, it could be a head in the second toss, it could be a head in both tosses. So it's a kind of a complicated event. Similarly, D is the event of getting at least one tail, so again it's at least one tail. So again, it is kind of complicated event, and it is not clear a priori, intuitively even, whether they should depend on each other. And so to guide us, we have probability theory and we have defined a concrete notion of probabilistic independence. So let us calculate the events, calculate the probabilities of the events, probability of C, probability of D, and probability of C intersection D, and check if the independence equation holds. Okay. So what is the event C? So the sample space again is HH, HT, TH, and TT, because these are two tosses of a fair coin. And all the outcomes are equally likely because it's fair, completely fair scenario. Let's see with the event of getting at least one head. So it is HT, which contains one head, TH, which contains one head, and HH, which contains two heads. So in particular, it contains at least one head. So these are the outcomes which favor C. So the probability of C is 3 outcomes over a possibility of 4, so 3 out of 4. Similarly, the outcomes which favor D, which is getting at least one tail, are HT, TH, and TT. So the probability of D is any of these 3 outcomes out of total 4 possibilities, so 3 out of 4. And what is C intersection D? It is getting at least one head and getting at least one tail. So if you get at least one head and one tail, if you get at least one head and at least one tail, and you have only 2 tosses, well, then either the first one has to be head and the second one tail, or the other way around. So the only possibilities which satisfy at least one head and at least one tail are HT and TH. So the probability of C intersection D is any of these 2 possibilities divided by a totality of 4 possibilities, so this is 1/2. So now let us check the independence equation. What is probability C intersection D? This is 1/2. What is the probability of C? 3/4. Probability of D? 3/4. If you multiply, you get 9/16, and 1/2 is 8/16. So 9/16 is not the same as 8/16. So these two events are not independent. So in other words, the information that C has occurred affects the chances that D might have occurred. So if you are told that at least one head has turned up, it affects the chances of seeing a tail. Okay. So and let us try to intuitively reason why this can be the case. Well, there are 2 slots, 2 tosses. Suppose you are told that at least one of them is a head. That means already at least one of the slots has to be H. Of course, so this should intuitively decrease the chances of having a T, right? because if you were given no information, no prior information, then you could have a T in any of these two slots. You could even have both the slots having tails. However, if you are told that at least one of them is a head, that means the possibility of having both of them as tails, which favors the event D, that there is at least one tail, is out of the window. So you are having to work with restricted less number of possibilities. So intuitively this should affect the chances of having a tail, and it should decrease the chances of having a tail, right? So again, intuition is going parallel to mathematics. Any questions? So let us continue with independent probabilities of independent events. So loaded coin is tossed 5 times. So the probability of head is 0.6. Probability of tail, therefore, is, so probability of head is 0.6. So what is the probability of tail? Well, the coin is either head or tail, and so probability of tail is just 1 minus the probability of head, right? So this is 1 minus 0.6, which is 0.4, because head is essentially, tail is essentially the complement of head, right, in this experiment. So probability of tail is just 1, is the other possibility, is the only other possibility than head, so it's 1 minus 0.6 or 0.4. So with this background, the tosses are independent. The coin is tossed 5 times, the tosses are independent, and you are asked to calculate the probability of getting all these possible scenarios. Okay? So what is the probability all tails? So it is T, 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 exactly 5 times. So it's the probability of having tails in each of the tosses, so it's 5 T's. Now the tosses are independent, so you should think of these as probability of T in the first toss, intersection T in the second toss, intersection blah 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 T in the fifth toss. So of course these are independent events because because the tosses are independent of one another. So the probability of the intersection is the product of the probabilities, and each of them is 0.4. So their product is 0.4 to the 5. So the probability of having all tails is 0.4 to the 5, which you can calculate to be 0.01024. Okay. Any questions? Okay. So let us now calculate the probability of getting at least one head. So again, so these are the usual sort of games with probability which one figures out as soon as you go through some examples. So of course, getting one head, if you try to calculate the probability of getting one head, so naively you might try to sort of calculate how many possibilities there are which contain at least one head, and then divide it by the total number of possibilities. But the point is that there is a much easier way to do it, which is to notice that at least one head is the complement of the event that all the tosses are tails. So at least probability of at least one head is just 1 minus the probability of having all tails. And probability of having all tails we just calculated, so you just slot it in to this equation and get probability of at least one head is 0.98976. Okay? Any questions? So now let us calculate the probability of getting exactly one head. Well, if you get exactly one head, then these are the only 5 scenarios. So, and these are of course disjoint events because they cannot occur together. So probability of getting exactly one head is the sum of the probabilities of these configurations of these outcomes. So the probability of getting exactly one head is the sum of the probabilities of these specific outcomes, and each of these specific outcomes has the probability that is as follows. So we now want to calculate the probability of each of these specific outcomes. Okay, so let's take the second one, for example, and notice that these are independent tosses. So probability TH TTT is nothing but probability T times probability H times probability T, probability T, probability T, because the tosses are independent. And now we are in good shape because we have already calculated probability head to be 0.6 and P of T to be 0.4. Slot it in, and notice that actually all these probabilities have the same value because of the similar argument, and you just get 5 times 0.6. So 5 because there are 5 terms here, and 0.6 because of the head, and 0.4 to the power of 4 because of the tails, and you get 0.0768. Okay? Any questions? Okay. So now let us go to a bit more complicated event. So exactly 2 heads. What is the probability of getting exactly 2 heads? So again, what we will do is that we will enumerate we will just look at, figure out what outcomes favor exactly 2 heads, and then we will calculate the probability of each such outcome and add them up. Okay? So how many ways can you get? So the results of these 5 tosses of the coin are strings of length 5, where each slot is filled with an H or a T, right? That's the experiment that we are talking about. And exactly 2 heads means that in these 5 slots, there are exactly 2 H's and there are 3 T's, right? So how many such configurations are there? There are basically, you basically need to, it's basically the same as the number of ways of slotting in, picking 2 spots for slotting H's. Once you pick 2 spots for slotting in the H's, in the remaining 3 spots you can just slot in tails and you will be done. So how many of these terms are there? There are 5 choose 2 terms in total, right? Because picking the 2 spots for your 2 heads. What is the probability of each of these configurations? Where there are 2 heads. So again, each of them splits as the product of the probabilities of the individual outcomes because of independence. So that's where we crucially use independence here. And each of the each of these outcomes have the probability that of 0.6 whole square because of the heads, and 0.4 whole cubed because of the tails. So it's just 5 choose 2 times 0.6 squared times 0.4 cubed. So it's 0.2304. Okay? Any questions? So let us discuss a bit of a generalization of this concept. So suppose, in the previous example we discussed the possibility, discussed the random experiment where you have a biased, where you have a loaded coin or a biased coin with probability of head being 0.6, probability of tail being 0.4, and you toss it 5 times independently, and you look at the probability of various events, right? So that's what we discussed. So let us think of a situation which sort of generalizes this in a natural way. So here we will think of a coin which is biased, and the probability of head in each toss is P. So it's just the previous example with P is equal to 0.6. Okay? And now we are tossing this coin n times independently. N times independently. So it is exactly the previous scenario with P is equal to 0.6, probability of head in each toss being 0.6, and n equal to 5. So 5 independent tosses. Okay? So this is just a direct generalization of that in terms of the symbols n and p. So, and if you look at the last probability that we calculated the probability of exactly 2 heads. So you can generalize this by asking what is the probability of exactly k heads, where k is anything between 0 and n. Okay? So, and what we will do is that we will exactly calculate the probability of having k heads in the exactly the same manner as we did here. So we will notice that probability of having exactly k heads is the sum of all the strings with k h's and n minus k t's, t, so k h's, and so some string of n minus k t's and k h's, right. So for any such configuration, this probability will split as probability of tail to the power of n minus k, because there are n minus k tails, and probability of h to the k, because there are k heads. Okay? So all of these configurations of k h's and n minus k t's have the same probability, which is ph to the k and pt to the times pt to the n minus k. So it's exactly going to be ph to the k times pt to the n minus k, and you just compare with what we have here, ph 2 heads, so ph to the 2 and pt to the 5 minus 2, and in how many ways can, so that, and then you just sum this up, so you just multiply this by the number of such strings which have exactly k h's. So how many strings of length n are there comprising of h and t, so that there are exactly k h's? Well, you calculate it just like the previous problem. So out of the n possible slots, you pick k slots for putting in the h's, and the remaining slots you just put in t's. So it's the same, the factor here which was 5 choose 2 will now be the same as the number of ways of choosing k slots for your h's out of n total slots, and you can choose k slots out of n in n choose k ways. So it is n choose k times ph to the k times pt to the n minus k. Exactly for 2 heads in 5 tosses, just like we had 5 choose 2, so n was 5, k was 2, and p was 0.6. So n choose k times ph to the k, 0.6 to the 2, pt to the n minus k, 0.4 to the 5 minus 2. Okay? And exactly you notice that ph here is p, so this is n choose k times ph to the k, so p to the k, because ph is p, and pt, probability of tails, is 1 minus the probability of heads, so it is 1 minus p, and this is to the power n minus k. Okay? Okay, so this is a good point to take a break, and after we return, we will continue with more problems. Okay, so let us continue with probability. So before the break, we studied binomial distribution, which is the random experiment where a coin with bias p, so a coin, loaded coin with probability of getting a head in each toss being p, is tossed. Such a coin is tossed n times independently of each other, and we notice that the probability of getting exactly k heads is n choose k times p to the k times 1 minus p to the n minus k. Okay. So here is a, so any questions about the binomial distribution? So if you look at the number of heads, it is, this number of heads is said to follow the binomial distribution. Okay. So number of heads in such a situation is said to follow binomial distribution. So let us continue with probability. So let's take the example of a monkey. So a monkey types at random on a typewriter and produces a sequence of 1 million alphabets without spaces. So just keeps on typing. So divide this sequence into blocks of 6 letters, and you know there are exactly 1 million. So maybe there is some remainder after division by 6. So just forget those. It's going to be something between 1 and 5. So that small number of letters at the end we forget, and we just divide this sequence of 1 million alphabetic letters into blocks of 6 letters each. Assuming that the letters are produced independently of one another and each letter is equally probable to be typed out, find the probability that one of these blocks is a sequence genius. So here is the specific sequence of letters GENIUS. So you want the probability that one of these blocks is appears as genius. So 1 million letters in total, independently typed from the English alphabet, and divide into blocks of 6. What is the chance that one of these blocks is actually bears the word genius? So how many total blocks are there? There are 10,000 divided by 6, and you just take the quotient, ignoring the remainder. So that's 1, 6, 6, 6, 6, 6 blocks of letters. Okay. So what is the probability that a block turns out to be genius? So let us calculate the probability that a block of 6 letters typed independently is equal to genius. So again, all the letters are independent. So the first letter has to be G. This happens with probability 1/26. Independently, the second letter has to be E. So this happens with probability 1/26, and they're independent. So times. Independently of the first 2 letters, third letter is 1/26. So times 1/26. Independently of that, fourth letter is another 1/26. Fifth one is another 1/26. Sixth one is another 1/26. So in total, 6 1/26s multiplied with each other to give you 1/26 to the power of 6. That's the probability that a single block, single particular block, is equal to genius. So what is the probability that none of the blocks, so we are asked to calculate the probability that one of the blocks is genius. So that means that there is at least one appearance of genius in the monkey's type. So the way we will do it is what is often useful in probability, which is sometimes or often you are, it's better to calculate the probability of the converse of an event and not the event directly. So in order to the probability that compared to calculating the probability that one of the blocks is a genius, it's actually easier to calculate the probability of the complementary event or the opposite event, which is that none of the blocks is a genius. Okay, and then you just get the probability that at least one of the blocks is genius by subtracting that from 1, so you get that the probability that one of the blocks is a genius is equal to 1 minus the probability that none of the blocks is genius. Okay? And it turns out that compared to calculating the probability directly that one of the blocks is a genius, it's much easier to calculate the probability that none of the blocks is a genius. Okay? So this is because of independence, and we will see soon why. So the probability that a particular block is genius is 1 over 26 to the power of 6, so let's call that P. So now you think of this huge number, let's call this capital N, this huge number of blocks. So capital N blocks. And I want the probability that none of them is genius. So how can that happen? So the blocks are all independent. So the first block is going to be not genius with probability 1 minus P, because probability of being genius is P, so probability of being not genius is 1 minus P. Independently, the second block is not a genius with probability 1 minus P, so times, because they are independent blocks. Similarly, independently, the third block is not a genius with probability 1 minus P, and blocks are independent, so again multiply, and so on, until the last block, which is independently not genius with probability 1 minus P. Okay? Because we want the probability that none of the blocks is genius, so individually each of these blocks must be not a genius, right? So the probability of that, as we just calculated, is 1 minus P multiplied with each other capital N times, where capital N is the number of blocks. So it's 1 minus P to the power of 1 followed by 5 sixes, which is the value of N. So this is so this is if you simplify, this is going to turn out to be approximately 0.994606. Okay, and there are certain calculational tricks which you can do. So you write the P as 1 followed by 5 sixes, divided by 1 followed by 5 sixes, so this is exactly the same thing, and then you use this approximation to see that this is roughly e to the minus 1 followed by 5 sixes times P, and then you can approximate this as 0.994606. Okay, and the calculation is not that important, but understanding the concept is very important. Okay, now so this is the probability of no block being a genius, and then you calculate the probability that at least one of the blocks is a genius by subtracting this probability from 1. So the probability that at least one of the blocks is a genius is 0.00054. Okay, so pretty low, 0.05%. Okay, any questions? So let us now move on to conditional probability. So conditional probability, so we actually have already, just to motivate, we actually have discussed already in today's lecture a bit about the kind of things which lead to conditional probability. So we noticed that in the experiment of tossing 2 coins and considering whether getting at least one head and getting at least one tail are independent events, we noticed that if you reason intuitively, then if you are given the information that there is at least one head, that should intuitively reduce the chances of getting at least one tail, right? Because it excludes some of the possibilities which lead to at least one tail. So therefore, what we see is that if you are doing a random experiment and you are given, if you are given the information that certain event has happened, that might affect the probability of other events happening. Okay, it might reduce the probability of other events happening. So for example, in the case of the coin toss, getting at least one head might reduce the probability of getting at least one tail, right? So so this is the notion of conditional probability, this is the following situation where you are doing you have done a random experiment. You did not observe the outcome directly. So, various events might have occurred, and you know that these events occur with various probabilities. Now you are told that a certain event has occurred. This does not force other events this does not prevent other events from occurring. Other events also might occur, but the information that this particular event B has occurred will update the probabilities. This information will enable you to update the probabilities of other events happening. So this is the notion of conditional probability. So given that then event B has occurred, you should update the probability that another event A can occur in the following manner. So probability of A given B. So this is denoted as a probability of A that given B. This notation is called probability of A given B is equal to probability of A intersection B divided by probability of B. Okay. So it's in a sense, if you think of these events as sets of outcomes, then the information that B has occurred restricts you to the outcomes, only to the outcomes which favor B. So if you are told that B, so you are not shown the outcome of the experiment, but you are told that B has occurred. That means you do not directly know which outcome has occurred for the experiment, but you know that one of the outcomes which favor B has occurred. This much you know, right? So effectively, the consideration of any other event will now be restricted only to those outcomes which favor that event and also favor B. So the outcomes which favor an event A and also favor B are A intersection B, and the outcomes that favor B are B. So the updated probability should be the probability of A intersection B divided by probability B. So in a way, you are just shrinking the total sample space to B, because the information that the event B has occurred tells you that only the outcomes that are favorable to B need to be considered for studying this random experiment further. Okay? So what happens when A and B are independent? So if A and B are independent, then probability A is same as probability A given B, and it's the same as probability A given B complement. So let us check why this is the case. So A and B are independent implies probability A intersection B is probability A times probability B. So this implies that probability A intersection B divided by probability B is probability A. But probability A intersection B divided by probability B is exactly probability of A given that B has occurred. So probability A given B is equal to probability A, which is exactly this. Okay. So if A and B are independent, that means that probability A given B is equal to probability of A. So intuitively what does that mean? That means that if A and B are independent events, then if you are given the additional information that B has occurred, it does not affect the chances of A occurring. Right? If you are told that B has occurred, it does not update, it does not change the chances of A occurring in any way. So that's somehow intuitively that sits very well, being two events not depending on each other. The information that one of them has occurred does not affect the chances of the other event occurring in any way. And this is also equal to the probability that of A given B complement. So why is that? So let us do some simple calculation. So A and B are independent, so A intersection B probability is equal to PA times PB. So let's subtract this from probability of A. So probability A minus probability A intersection B is probability A minus probability A times probability B, right? Now, what is probability A minus A intersection B? So if you think of the set A and if you think of B, so this is A intersection B. So A minus A intersection B is this other shaded region, so this is exactly A intersection B complement, right? So probability A, which is the total area of A, minus the probability of A complement, which is this intersection, is equal to the probability of this area shaded is a area shaded in the other direction from A intersection B. So it's the probability of A intersection B complement. Okay? And this you can take probability A common. So this is 1 minus probability B. But 1 minus probability B is nothing but probability B complement. So you get probability A intersection B complement equal to probability A times probability B complement. So what did we do? We started with A and B independent events, and we noticed that, so that means that probability A intersection B is equal to probability A times probability B. And now we did some simple manipulations and showed that this necessarily implies that probability A intersection B complement is equal to probability A times probability B complement. So if A and B are independent events, then if you look at the events A and B complement, they are also independent. Okay? And you know, this is natural because in some sense this is intuitive, because A and B being independent, so B complement is exactly not B, right? So we already noticed that A and B are independent means that is the same as saying that the information that B has occurred does not change the chances of A occurring in any way. Well, B complement has occurred means that B has not occurred, right? So again, it's more or less the same as updating on the status of B, and independence, as we already noted, tells you that updating you on the status of one event does not affect the chances of the other event occurring. So again, you can take the B complement to the other side and get probability A intersection B complement by probability B complement, which is the same as probability A given B complement is equal to probability of A. Oops. Is equal to the probability of A. Okay? Probability probability of A given B complement is the same as the probability of A. Okay? Any questions? Okay, and similarly you can interchange the roles of A and B in this, and you can get the other equations. Okay. So let us look at let us continue with conditional probability. So let us see some example. So suppose two fair die are tossed. Find the conditional probability of getting a double. So the tosses on the two die have the same outcome, given that the total score exceeds 10. So how many outcomes? What are the outcomes which favor a double? So the tosses on the two coins have to be the same. So it should be 1, 1 or 2, 2 or 3, 3, up to 6, 6. So there are 6 possible outcomes which favor this. Favor A. What is the outcome? What are the outcomes which favor B? So the total score has to be 10. So it can only be as much as 12, right? Because at most you can have 6 on each toss. So at most it could be 12. So if the total score exceeds 10, then the total score must be 11 or 12. So it could be 11 in 2 ways, 5, 6 and 6, 5, and it could be 12 in only one way, which is 6, 6. So this is B. So now we have listed all the outcomes favorable to A and B. So what is probability A given B? It is probability A intersection B divided by probability B. So what is the probability of A intersection B? So A intersection B is only one event, one outcome, 6, 6. So one possibility out of total 2 tosses of coins 2 tosses of dice, so out of 36 possibilities. So this is 1 over 36. And what is the probability of B? There are 3 possibilities out of total 36, so 3 over 36. And 36 cancels, and you get 1/3. So given that the total score exceeds 10, the chance that you get a double is 1 in 3. Okay? Any questions? Any questions? Okay. So let's take another example of conditional probabilities. So Tan has 3 children. You know that he has at least one son. What is the probability that the first child is a son? So in each, for each child, it's equally likely to be a son or a daughter. And there are 3 children, and you know that you are given the event that there is at least one son has occurred. So you want to find the conditional probability that the first one is a son. So what is the sample space? So now son is S and daughter is D. So you have various combinations of length 3 of the letters S and D. They are equally likely. So what is the probability that the first is a son? So that means that the first letter is S and the other letters could be anything, right? So what is the probability of this? These are independent. So probability of S times probability of getting S or D times the probability of getting S or D, right? Probability of S is 1/2, and probability of getting a son or a daughter, well, that's 1, right? Because that's anything essentially. So probability of getting a son is 1/2. In the probability of getting a son in the first kit is 1/2. What is the probability of getting at least one son? Well, probability of getting at least one son is again 1 minus the probability of B complement, which is no sons. And this is the one that is easier to compute. This is probability of 3 daughters. So this is 1 minus probability of daughter, probability of daughter, probability of daughter in the third place. So this is 1 minus 1/2 cubed. So this is 1 minus 1/8. So this is 7/8. 7/8. And when you do the calculation, it is 4 over 7. So given that at least one is a son, the first one is a son, the probability of having the first one as a son is 4 over 7. And notice that 4 over 7 is bigger than 4 over 8, which is 1/2. So if you were not told that there is at least one son, the probability of having a son as the first child would be 1/2, which is 4 over 8. And that is smaller than the conditional probability of having the first child as son, given that at least one son. So given the information that there is at least one son somehow increases the chances of the first child being a son. Okay? Any questions? So let's now go on to probability trees. So while computing probabilities involving a sequence of experiments, we can use a probability tree to keep track of outcomes. So the probability, and the rule is that the probability of arriving at a destination is the product of the probabilities along a path. Okay? So tossing for example, you toss a coin 3 times with the probability of head being equal to P. So in the first toss, you could get either H or T. So you are encoding the tosses of the coin, outcomes of the various tosses of the coin as a binary tree. So if you follow this route, your 3 tosses will read HTH. If you follow this route, it is going to read HHH. If you follow that route, it's going to be THH, right? So that's the coding. And so this destination is the summary of the path that you have taken. And of course, to calculate the probability, you just multiply, and you can check that the probability of any of these paths, which is any of these corresponding strings, is the product of the probability of that you have encountered on the paths. Okay, and you place the probabilities on these paths by placing a P if the next one is H, or placing a Q if the next one is T. Suppose you are here, it has two branches, one H, one T. For H, you place a P, which is the probability of getting a H, and place a Q if you get a T, which is the probability of getting a tail. Okay, and every destination is equivalent to some path, and this path encodes a string, and the probability of this string is equal to the product of the probabilities on the path, on the edges of the path. Okay, so that is the correspondence. So suppose you have tossed two dice. If a double is tossed, throw two fair coins, otherwise throw one fair coin. Find the probability of getting no heads. So again, dice, you throw a dice, or you have thrown two dice. So the first, so it's a two-stage random experiment. So in probability trees are particularly useful in understanding multi-stage random experiment. So this is a two-stage random experiment in the example here. So you can, in the first stage you toss two die, and if the result of the two dice is a double, so the same number appears on both, you throw two fair coins, otherwise you throw one fair coin. And finally, the event whose probability you want to calculate is just depends on the final stage, right? But it's difficult to get your hands on the event which is just depending on the final stage, because what happens in the final stage is depending on what had happened in the first stage. Okay, so that's why it's useful to deal with it in terms of a tree. So let D be the event that you get a double in the first slot in the first round. So you encode this random experiment in terms of a tree. So in the first round you could get a double, or you might not get a double. You get a double with probability 1/6. So D is for double. So you put two edges out of this. So one edge leads to D, and you put 1/6 on this, which is the probability of getting a double. And the other edge is D complement, so no double, and that probability is simply 1 minus 1/6, which is 5/6. Okay. Now if you get a double, you throw two fair coins. So each of them happens, so two fair coins, so possibilities are HH, HT, TH, and TT. So the probabilities you can calculate, they are two fair coins, so they're independent. So this is 1/4 for each. And if you do not get a double, you just throw one fair coin, so you get a H or a T with probability half each. Okay, so this is the description of the tree. So now, what is the probability of getting no head? So no head means either TT here or just a T here, and you calculate the probabilities of these possibilities by multiplying the probabilities on this path and adding it with the probability of this eventuality is the product of the probabilities on this path, and you want the probability of either this or that, so you sum up these two products. Okay, and get 11/24. Any questions? Okay. So let's now look at probability trees, another example. So 20% of the patients of a clinic are smokers. Suppose that the probability that a smoker has a respiratory problem is 0.7, pretty high, whereas a non-smoker has a respiratory problem is pretty low, that probability is 0.25. What is the probability of that a patient at a clinic has a respiratory problem? So so you look at a random patient, and you want to see that, so you look at a random person, you want to see the chance that he has a respiratory problem. Now you do it as follows. again as a two-step random experiment. So first you classify the person as a smoker or a non-smoker. So there are certain chances of being a smoker and certain chances of being a non-smoker. So S is for smoker. So S and S complement. So smoker or non-smoker. So smoker with probability 0.2, non-smoker with probability 0.8. And now respiratory problem is denoted by R. So R or R complement. So if you are a smoker, then respiratory problem occurs with probability 0.7. And so no respiratory problem with probability 0.3. If you are a non-smoker, then it's different. So respiratory problem occurs with probability 0.25. So no respiratory problem is 1 minus 0.25, which is 0.75. So now you want to find the probability of a random person being having respiratory problem. So you want this eventuality or that eventuality. So you follow from the start, you follow either this path or that path. Okay? So you sum up the probabilities of these two paths. And what are the probabilities of these two paths? This one is 0.2 times 0.7. And this one is 0.8 times 0.25. And you multiply them and add them up and you get 0.34. Okay? Any questions? So Monty Hall game, let us revisit the Monty Hall game. So the Monty Hall game, if you remember, was as follows. So you pick so there are 3 doors. Behind each door there is a goat or a car. So you have to pick a door. So you have to, your goal is to pick a door which has the car. That's your goal, and you want to maximize the chances of that. And you do it in 2 stages. So already 2 stages means there is a chance of getting a probability tree here. So if you first choose a door. So since there are 2 goats, then the remaining 2 doors, at least one of them must contain a goat. So the game show host then comes and picks one of the other 2 doors which contains a goat, so that it contains a goat, and opens the door and shows you. So now you have one door selected, but it is closed. You don't know whether it contains a car. You have a second door which is open, which contains a goat, but you also have a third door which is closed. So there are 2 closed doors. You are holding on to one. So, and one of these 2 doors contains a car, and you want to choose the one which contains a car. You want to maximize your chances of choosing the one which contains a car. And the question is whether you should switch to the other door and whether you increase your chances of having the car by switching to the other door. So now let us look at the various probabilities. So door 1 is the door which you choose in the first round. So if the door 1, which is the door which you choose in the first round, contains the car, then the other 2 doors will contain goats, and it's reasonable to assume that the host will randomly open either of the 2 goat doors. Okay? If the door which you choose first contains a goat, then among the other 2 doors there is only one goat, and the host is forced to choose that door. In the third case, which is similar to the second case, so if the car is hidden behind door 3 and you choose door 1, well, then the host is forced to open door 2. Okay? So now, in the first case, if you switch, you lose. In the second case, if you switch, you win. In the third case, if you switch, you win. So And the probabilities of these are 1/6 each, and the probabilities of these two are 1/3 each. So if you go in the tree form, so you could, the car could be located behind any of these three doors, and if it is already behind door 1, which you have chosen in the first round, the host opens door 2 or door 3 with probability 1/2 each. So in this case, if you stay, you get the car. If you switch, you get the goat. In the second possibility, the car is behind door 2, and the host opens door 3 with probability 1. So the total probability of this, according to the probability tree, is 1/3. And if you stay, you get a goat, and you benefit if you switch. Similarly, for the third possibility, when the car is behind door 3, so the probability of winning is, if you switch, you win in these two possibilities, and these two possibilities happen with probability 1/3. So the probability of winning, and you do not know a priori in which of the branches you are. So if you switch, you win, you gain if you are in these two possibilities, and the total possibility and the total probability of being any of these two branches is 1/3 plus 1/3, which is 2/3. So in the Monty Hall game, if the host chooses randomly between the two goats, if you are on the right track, then the probability of, in the Monty Hall game, the probability of winning if you switch your choice from away from the door 1, which you had chosen in the first round, is going to be 2/3. So you actually improve your chances by switching. Okay? Any questions? Okay, so if there are no further questions, let us end here today, and we will continue next week.